So, good evening and welcome you all to the guest lecture session of day 3. And it's a pleasure having Professor Satyonarayan Mukhopadhyay from Indian Association for the Cultivation of Science, Kolkata. And he is going to talk on a tutorial on the effective Lagrangian for Goldstone bosons. And all right, so with that, let us start.
I had started working on effective field theories right after the Higgs discovery in 2012, uh, and we wanted to see if the operator structures deviated from the standard model predictions, how they affect the Higgs events, in particular the kinematics. And subsequently, I also worked on effective theories for dark matter later on. Uh, while recently I haven't really actively worked on effective theories, but when Subodha asked me to give a lecture, I thought let me go back to old times, and the oldest I could go back was the 1960s, when really the idea of effective theories were coming into play. In fact, there is a very nice story recalled by Steven Weinberg, who was one of the pioneers in this field. So at that time there was no QCD in 1960s, and at that time they were trying to understand the dynamics of hadrons and mesons at low energies. And the main tools, because strong interactions are strong, so they couldn't do perturbative quantum field theory, and many people were losing hopes about quantum field theory. So what they were doing instead was something called current algebra, so which was basically studying the symmetry properties of different currents, and from current algebra they were trying to deduce rules for scatterings of pions, nucleons, and so on. And Weinberg writes that he had worked out using current algebra the amplitudes for a single pion emission and 2 pion emissions and so on in scatterings. And the more and more pions you include in current algebra, the computations get messier and messier. And he recalls that one day he was sitting in a cafe and writing down the formulae he got for multiple pion emissions, and on a napkin, and by staring at the results for the scattering amplitudes that he obtained, it occurred to him that he can in fact write down a Lagrangian and a quantum field theory from which all those scattering amplitudes followed. And the Lagrangian looked rather funny. So the interaction, if I write down for the pions only, that he thought will give the correct results, was of this form. So this is in 1960s, and the interaction was of this form. Okay, so this was the Lagrangian, interaction Lagrangian. This is not something we usually write down when we do our basic quantum field theory course with the term v square minus pi dot pi in the denominator, right? But this rather funny looking Lagrangian reproduced all the results of current algebra, and this actually started the business of writing down low energy effective field theories which could describe pion nucleon scattering processes. At that time it was called phenomenological Lagrangians. Initially it was not called effective field theories. There is a very famous paper by Weinberg on phenomenological Lagrangians, and soon it was realized with the suggestion of Schwinger that in fact if one concentrated on the symmetries of the low energy interactions only and wrote down all possible terms allowed by the symmetries, then they should reproduce the results of the scatterings. And this is what we usually nowadays routinely say, right. The whole point of this effective field theory business is just you have your low energy fields and you know the symmetries and you write down all possible operators that you can between those fields that obey those symmetries. That is what you have been doing for the last 2 days. And so this was the beginning of such things, and there are reasons to believe that these pions were actually Goldstone bosons of certain broken symmetries. You might remember that pions are much lighter than all other hadrons. So people wondered already then that why is pion so much lighter than the other hadrons, and Nambu actually proposed that pions may be the Goldstone bosons of a broken symmetry, and this understanding actually led to this Lagrangian that I wrote down here. And in today's tutorial we shall try to understand how this Lagrangian comes about. Okay. So we will focus on the effective low energy Lagrangians for Goldstone bosons, and these are not just useful for describing low energy pion dynamics, they are useful for electroweak physics, which also you have been doing. As you know, in electroweak theory also you have Goldstone bosons, and it will be the same Lagrangian. So the Lagrangian that describes pion physics will be exactly the same Lagrangian that describes Goldstone bosons in electroweak theory, standard model electroweak theory. And so this is a very broad subject. In fact, the Goldstone boson effective Lagrangian actually shows all the features of effective field theory that you have been discussing so far. Now I wanted to actually begin with this simple classification of these broad classes of effective field theories. One, excuse me, I might have to sit to write, but sometimes I will stand up, sometimes I will sit, because writing while standing is really difficult on this tab, and the board is very small. So broadly there are two types of effective field theories. One for which you already know the UV physics, and you can do a perturbative matching. Okay, you have been learning about that as well from lectures by Jose, Shubho, and Joydeep. And so I don't know where is the eraser, but anyway. And the other type is where you actually cannot do the matching. Now you cannot do it either because you do not know the UV theory, or because you cannot compute things in the UV theory, right. So the examples of the first type, where the UV physics is known and you can do perturbative matching, is for example the 4 Fermi theory, right, the classic example of effective field theories for which the UV theory is the standard model. Okay. And there are also things like heavy quark effective field theory, where you describe mesons with one heavy quark, or this non-relativistic effective field theories for QED and QCD. So those are theories of bound states like the Onia. And the other type, which I said, where you cannot do the matching, either because you do not know the UV theory, or because it is too complicated to compute, maybe it is too strongly interacting. Now the examples for where you do not know the UV theory is the standard model itself. So there you do not try to match to any particular UV theory, you just write down all the possible operators that you can, right. You do not try to determine the coefficients by matching to some UV theory, or the Einstein theory of gravity, right. There also you do not know the UV theory, you can in principle actually go beyond Einstein's theory of gravity and write down all possible terms which are general coordinate invariant, right. So, that will be an effective theory at low energies where you do not really know the coefficients, you cannot match to AV theory. And the other class is where, as I said, that the matching coefficients are not calculable perturbatively, right. And the example for that is QCD, right. So, if you start with QCD and from QCD you want to obtain the low energy dynamics of pions and mesons, that is not possible because QCD is strongly interacting and you cannot really match these two theories unless you do non-perturbative physics, right, unless you go to lattice, right. So, it is the second this last class that is business in pion physics, right, where I know the UV theory which is QCD, but I cannot do a matching. So, I have to entirely rely on the symmetries of the low energy theory. Okay. And in order to discuss how this Goldstone boson effective Lagrangians look like before I go to pions, let me start with a very simple model where these features are all very clear. So, as I mentioned, for Goldstone boson physics, the main thing is the symmetry breaking pattern, right. So, there is some large global symmetry G which is broken to some other global symmetry H, spontaneously broken, which gives rise to Goldstone bosons, right. You have all studied about Goldstone's theorem, and the whole point of Goldstone boson effective theory is that this symmetry breaking pattern determines the low energy Lagrangian completely. So, you just need to specify what is G and what is H. You do not even need to specify how the symmetry is exactly broken. Okay. For QCD, for example, we do have guesses, but no one knows for sure how the symmetries are, global symmetries of QCD are broken. And just this symmetry breaking pattern decides the physics, low energy physics of Goldstone bosons. And because the symmetry, this global symmetry group G and H are the same for this standard model electric theory and for QCD with two flavors, that is why the low energy Lagrangian for pions will exactly be the same as those for the Goldstones in the electric theory. So, that is what it is. So, let me then start by discussing this very simple model of spontaneous breaking of global symmetries, which I am sure all of you have studied earlier, but it is good to go through it again. So, spontaneous symmetry breaking of global symmetries. Well, so, the model that we will study is the so called sigma model. So, consider 4 real scalar fields which I will put in a multiplet. So, phi is sigma, pi 1, pi 2, pi 3. These are all real scalar fields, and they are described, the dynamics is described by a Lagrangian, which is the kinetic term minus the potential, which takes this very simple form, okay. So, this is the Lagrangian, 4 real scalar fields organized in a multiplet satisfying the dynamics is governed by this Lagrangian, okay. Now, if this, so first of all, can you tell me what is the global symmetry of this Lagrangian? SO4. So, as you can clearly see that if you make a rotation among the elements of this multiplet phi I goes to Rij phi j, where R transpose R is identity, then this Lagrangian remains invariant, right. So, it is a rotation of these 4 components, right, and this rotation group is SO4. So, R belongs to SO4. Now, there are 2 situations that are possible. One is that V square is negative, right. If V square is negative, the minimum is at phi equal to 0, all the components are 0, right. So, this describes 4 fields of the same mass, and that is it. The minimum is at 0, and the minimum still has a symmetry of SO4, right. If you are sitting at 0, you do a rotation, you still will sit at 0, right. So, the vacuum has SO4 symmetry if V square is negative, right. The interesting things happen if V square is positive, right. So, for V square positive, the minimum of the potential is for phi transpose phi equal to V square, correct. So, this is infinitely degenerate set of minima, right. There are infinitely many solutions that are possible, and they are given by this equation. So, let me put this symbol for the vacuum expectation value, and that is V square. So, these are the set of minima. Now, to do our quantum field theory, we need to choose a vacuum, right. So, choice of vacuum around which we will study fluctuations. So, choice of vacuum, this is arbitrary, of course. Let me make a choice where, yeah, somehow this is okay. So, let me make a choice which is expectation of phi equal to V 0 0 0. Okay. So, which means I have put the vacuum expectation value in one particular direction, right. Because of SO4 symmetry, whichever direction it is, I can orient it to one particular direction. So, this is without the loss of any generality. Okay. Now, does this vacuum have SO4 symmetry? No, because if your SO4 rotation touches this first element, then the vacuum will not remain invariant, right. So, this vacuum does not have SO4 symmetry. What is the symmetry of this vacuum? SO3. So, if I make a rotation of this among these last 3 components, right, the vacuum will still remain a vacuum. So, the symmetry of the vacuum is SO3, not SO4. Okay. So, symmetry of vacuum, and I shall denote the symmetry of the vacuum by H. Right, this is the symmetry of the vacuum. Okay. So, the symmetry breaking pattern then is from SO4 to SO3. Now, how many generators are there for SO4? Huh? Not sure? SO4, how many generators? 6? No, not for you. No, I really want them to participate a little bit, right. So, it has 6 generators, right. It is n into n minus 1 by 2, right. So, there are 6 generators, and SO3 3. So, the number of broken generators is 3. And by Goldstone's theorem, how many Goldstones should be there then in this theory? 3, right? Number of Goldstones equal to number of broken generators, right? So this is the number of Goldstones. Okay. So far so good. So we have 3 Goldstones. Now let us define a shifted field as you usually do, because we do our field theories around fields with 0 vacuum expectation value. So this sigma hat field will have 0 vacuum expectation value. It's just a shifted field, right? So define sigma hat as sigma minus v and rewrite the Lagrangian, right? So in terms of sigma hat, the Lagrangian will be the kinetic terms right, and a mass term for the sigma field, which is given by twice lambda v square, which you can easily check, plus some interaction terms m square over 2v sigma hat into sigma hat square plus pi square and minus m square by 8v square sigma hat square plus pi square whole square, right? This you can easily check. So take the old Lagrangian, substitute sigma hat equals to sigma minus v, and you obtain this Lagrangian, right? So what we see is that the sigma field has a mass 2 lambda v square, and the pi fields do not have masses, as we expected, right? They are Goldstone bosons, they are massless, right? Now with this Lagrangian you can derive the Feynman rules of interactions between the sigma and the pi fields and compute scatterings between these Goldstone bosons, pi pi to pi pi scattering, right? So I want you to do this exercise. So there will be some exercises because it's a tutorial. So the first exercise is compute pi pi to pi pi scattering, 2 pi into 2 pi scattering in L sigma, so in this theory, okay. And after you compute it, expand in powers of energy over mass. Expand in powers of energy is energy of these pions and mass is the mass of the sigma, energy over mass, and determine the leading behavior in powers of E. Once you expand, you will know all the behaviors. This is a very important computation to do, okay. This is a very simple Lagrangian. You have cubic and quartic interactions. Just compute the pi pi to pi pi scattering, but remember to include all the channels, okay. So when you do sigma exchange, you will have STU channel, all of them are important, okay. Just compute this and expand it in the power series in E over M, okay. So now we change gears. This is simple, this was just a review, and I change gears by doing something called a field redefinition. Now it is not as simple as it sounds. There is a theorem in quantum field theory. Many people worked on this topic in again the 1960s. It's famously known as Huck's theorem, but there are others also who worked on it. And in the context of Lagrangian field theories, it was Sidney Coleman who showed that if you have a theory which is defined by a Lagrangian, let us say theory of scalars to begin with, it is defined by a Lagrangian which is a function of the scalar fields and the derivatives of the scalar fields, and then you make a field transformation. So you define new fields phi prime which are functions, I am writing the inverse transformation, but that is equivalent, which are functions of the old fields, okay. You can invert this to obtain phi prime in terms of phi, right. So you make a field redefinition and then you compute the transformed Lagrangian. So L prime phi prime del phi prime, which will be L of f of phi prime del of f of phi prime, right. So you compute now the Lagrangian in terms of the phi prime fields. In general, you will get a new theory, right. You will get a new Lagrangian, right, depending on what the field transformation looks like, right. And the Green's function will also be different. So now if you compute Green's function, different Green's functions, they will all be different. But under certain conditions, the S matrix elements that you obtain by using these two theories will be the same. And the conditions are a little bit technical. They say that the Jacobian determinant at the origin should be 1. The Jacobian determinant of this transformation at the origin should be 1. As long as that is true, right, then these two theories will give the same S matrix element. Remember, the Lagrangian is different, the Green's functions are different, but the S matrix elements will be the same as long as that condition is satisfied. Okay. So same S matrix elements. Under certain conditions. And what is even more important for us is that this statement holds order by order in perturbation theory. So it is not S matrix elements to all orders that you have to compute to get the same answer in the two theories, but order by order the S matrix elements will agree. Okay. This is a non-trivial result, and I urge you to check that by doing a simple exercise. Take a free scalar field theory to begin with, right. So take a free scalar field theory, del phi square minus del phi square by 2 minus m square phi square by 2. This is a free scalar field theory, and make a nonlinear transformation. So define new fields such that phi is some constant plus chi whole square. This is a field redefinition. Okay. You plug that in. Now you will have interactions between chi. The old theory was free theory, no interactions. But in the new theory, you have terms like chi cube and chi to the 4th. Those are interactions between chi. So now compute chi to chi scattering in this theory. What should you get? Suppose this transformation is a good transformation, the Jacobian determinant is 1 at the origin. What? No, where is derivative coupling coming from? A is a constant. Yeah. What do you expect to get based on just the theorem that we discussed? Right. 0. You should expect to get 0 because it's just field redefinition from a free theory. But it's rather important to do this computation and see that you actually get a 0. So it's a non-trivial computation. Okay. So please do it. Okay. We need this result again and again, right. What I want to emphasize is field redefinition is not as simple as it sounds. Okay. If you want to look at the proof of this theorem, there are papers by Coleman, Sidney Coleman, for Lagrangian field theories that you may look up. Essentially, you have to go and look into the path integral first and so on. But anyway, so with that out of the way, I will start now doing field redefinitions, right? Because this theorem makes field redefinitions legitimate as long as they are proper. So let me start by doing a simple field redefinition. Define a complex field which is a matrix. Capital sigma of x is small sigma of x times the 2 cross 2 identity matrix plus I tau dot pi of x. These taus are the Pauli matrices. Okay. This is a field redefinition. Sigma is now a complex field, and it is So, I am now making a field redefinition.
But what is the reason that you wanted to write it in this way?
Yeah, this it will become clear. Okay, at the moment it is just a field redefinition because it is legitimate to do field redefinition as long as the Jacobian is 1 at the origin. So, this is a complex field now and it is matrix valued, and I claim that the Lagrangian for this should be, so you have to do the transformation of course, but I claim that the Lagrangian is 1 over 4 trace of del mu sigma dagger del mu sigma minus lambda over 16 trace of sigma dagger sigma minus 2 v square whole square. Okay, this is the claim. So, the claim is that this Lagrangian is same as the old Lagrangian with this field redefinition in view, right. You can very easily check this as long as you remember what is the trace of two Pauli matrices. Do you remember what is trace of tau A tau B? These are Pauli matrices. Anybody from the younger? Huh? It's actually twice delta AB, not delta AB. It is a trace, right. When you multiply, you get an identity matrix, but then you take a trace, right. So, it is twice delta AB. So, as long as you remember this trace, you can easily verify that this Lagrangian is same as the original Lagrangian that we started with. So, under the field redefinition, this is the Lagrangian. Okay. It is very easy to do, just take this trace. Okay. Now, let us figure out the symmetries of this Lagrangian. Okay. What are the symmetries of this Lagrangian? I claim that the global symmetry of this Lagrangian is SU2L cross SU2R, where these L and R's are just some labels, they do not mean anything at this stage. Okay. There are two independent SU2s and the global symmetry is a product of these two, okay. That is the claim. And under this symmetry, the sigma field transforms as follows. It is GR sigma GL dagger, where this GR and GL are the SU2 matrices. So, GR belongs to this SU2R, these are independent SU2s, and GL belongs to this SU2L. Okay. It is very easy to check that this is a symmetry, right, because once you put this inside this trace, right, what will happen? So, if you have trace of sigma dagger sigma, this will go to trace of GL sigma dagger GR dagger GR sigma GL dagger, and this GR dagger GR is of course 1, and now I need a property of trace to know that this is a symmetry, the cyclicity of the trace, right. So, trace are cyclic. So, if I can take this GL here by the cyclicity of trace, and then this is invariant, right. And as long as sigma dagger sigma is invariant, del mu sigma dagger del mu sigma is also invariant, because these are global symmetries, they do not depend on space times, so they do not care about the derivatives, right. So, the symmetry of this Lagrangian is SU2L cross SU2R, that is the global symmetry. Okay. Now, you might wonder, I mean we had started with the Lagrangian with an SO4 symmetry, but now you have made some complex combination of those 4 fields and you claim that the global symmetry is SU2L cross SU2R, right. Now, there is a mathematical result that helps us understand this point, that if you consider the Lie algebra of these two groups. So, consider the Lie algebra of SO4, which I write as small SO4. This is same as the Lie algebra of SU2 cross SU2. Okay, this you can check, and therefore, these two symmetries are essentially the same as far as the Lie algebra is concerned, as far as the algebra of the generators of the symmetries are concerned. Okay. And you can also quickly check that the number of independent transformations is also same, right. SU2 has 2 square minus 1, 3 generators. So 2 SU2s, so 3 plus 3, 6 generators, and SO4 also had 6 generators, right. So it is essentially the same symmetry, but because I have written in terms of a complex field, it appears in a bit different way. Okay. Now, having obtained this Lagrangian, let me make yet another field redefinition. So today's tutorial is all about field redefinitions, many field redefinitions. So one more field redefinition. Second one, where I go to polar coordinates. You will understand why I am putting so much effort in these field redefinitions. Okay. So you can write down any 2 by 2 matrix as a magnitude, so modulus times a phase, which is a unitary matrix. Right. So this is the decomposition of a 2 by 2 matrix, where this U is e to the power I over V tau dot phi. I have put the V to make the exponent of the exponential dimensionless. So phi is a scalar field, it has dimension 1. So I have divided by a mass dimension. The only mass dimension in the problem that we have is V, so I have just divided by V. It is arbitrary, but okay. So this is the new field. This is like polar coordinates. Right. Now U dagger U is 1. Can you tell me why? U is a matrix. So again, to the younger audience, why is U dagger U 1? Okay, so it's an exponential of Hermitian matrices. So that will give you the proof that U dagger is 1. Good. Now this is the transformation. Okay, the mapping is a bit non-trivial. This does not give the mapping explicitly, and given the time, I think I will give it as another exercise to compute the mapping. The mapping should be this: sigma of x is V plus S of x times cosine, this is a highly nonlinear mapping, mod phi by V, and pi of x is sine mod phi by V into phi x by mod phi. So it is a really highly nonlinear mapping. Okay. So your job is to prove that this is the mapping which gives this result. Okay. So you just need to invert this equation. Okay. Now, given that we know how sigma, this big sigma, transforms under SU2 left cross SU2 right, the question is how does U transform? Okay. U is the exponential of this pi's, right. Now, in order to see that, it's just sufficient to note that, so sigma, it just goes to gr sigma gl dagger under G. So you just note that in sigma I have a modulus V plus S of x, but this does not have any matrix indices. So this will just come out of the sigma, and all the matrix indices are contained in U, right. So it must be that U also transforms in the same way. You understand, right? Because these GR and GLs are matrices, right? They will act on some matrix indices, right? V plus Sx has no matrix index, right? So this field S is then a singlet under these transformations, and U transforms in this way. Yeah. Yeah. It must be, right? Because it multiplies the whole thing. Yeah, thanks. So if you did the exercise, you'll find out the errors. So please do them. Yeah, I don't guarantee that there are no errors. There may be errors. So please. Yeah. I just did some computations, right? I mean, I don't know. Okay. Okay. So all of you are fine with this. That under this global symmetry G, this exponential matrix U transforms as GRU GL dagger. Fine. Okay. Now, what is the symmetry of the vacuum? So the vacuum, all the vacuum expectation value has been put in the modulus part, right? So in the vacuum, all these 5 fields take vacuum expectation value 0, right? So in the vacuum, this U is an identity matrix, correct? So the vacuum expectation value for sigma is simply V times the identity matrix, correct? Because U is identity in vacuum, all the 5 fields are 0 in the vacuum. Now, is this SU2 left cross SU2 right a symmetry of this vacuum? What do you say? You can just check, right? How does it transform, right? So this will go to GR vacuum G left dagger. Identity will just go through. So it's V GR GL dagger. Is this one? It's not. So it's not V. So this full group G is not a symmetry of the vacuum. What is the symmetry of this vacuum then? Which one? L equal to R, right? So if GL was GR, then this is a symmetry of the vacuum, right? So symmetry of the vacuum is GL equal to GR, right? So it's one SU2, and this is known as the vectorial SU2. Let's call it SU2V. Okay. So the symmetry breaking pattern, so this is our H, right, is then SU2 left cross SU2 right going to SU2V, and there are 3 Goldstones as before, right? 6 in G, 6 generators in G, 3 in H. So there are 3 Goldstones. The number of Goldstones of course will not change, right? The physics will remain the same. It's just field redefinitions, right? So now with this compute, let us compute how the Lagrangian looks like, right? So remember our old Lagrangian, right? It was I can go up, so that's good. This one, right? 1/4 trace of del mu sigma dagger del mu sigma minus lambda over 16 trace of sigma dagger sigma minus 2v square, right? So you plug in this sigma v plus s of x times u of x in this, right? Because v plus s of x has no matrix indices, all the traces will act on u, correct? U has the matrix indices. So if you just plug this in, you will obtain 4 terms. In the part where we have trace of del mu sigma dagger del mu sigma, there are 4 terms to begin with. The first 2 are very easy. You will obtain del mu s trace of u dagger u plus v plus s whole square. You can almost read this off, right, just by looking at that Lagrangian del mu u dagger del mu u, right? The trace acts only on the u's. So these are the square terms. Now there are 2 cross terms, right? The 2 cross terms are as follows: del mu s trace of u dagger del mu u v plus s plus del mu s trace of del mu u dagger u. So, this is the del mu v plus s. Okay. Now, can you try to simplify these cross terms? So, of course, del mu s is common, v plus s is common. So, it is a sum of trace of u dagger del mu u and trace of del mu u dagger u. Can you see a simplification? It's kind of staring at you. No? Derivative of? Very good. So, it is derivative of u dagger u, right. So, if you add these two, you get trace of del mu of u dagger u, and you can take the del mu outside the trace, right. So, it is del mu of trace of u dagger u, but u dagger u is identity, right. So, this del mu of that is 0. So, these last two terms add up to 0, clear, right. U dagger u is identity, remember that, it is a unitary matrix, you understand, right. So, the last two terms will add up to 0 and we are left with these first two terms. The potential is very easy to calculate, just take trace of sigma dagger sigma, you will just get 2 into v plus s whole square because u dagger u is 1. So, what is our Lagrangian then? So, our Lagrangian after plugging all this in is as follows. So, let us start with this u part which contains the Goldstones, right. So, this term, remember there was a coefficient up front, right. So, this yeah, there is a 1 over 4 trace of del mu sigma dagger del mu, right. So, 1 over 4 was there. Okay. So, then we have, let me take a v square common. So, v square over 4 1 plus s over v whole square trace of del mu u dagger del mu u plus the Lagrangian which involves only the s field. You can easily check the mass term for the s and the whole Lagrangian for the s is actually the same as the one for sigma. In fact, if you have followed your lectures so far on the standard model given by Subhaditya, you should be able to recognize this Lagrangian for s. Does this look familiar? The Lagrangian for s, just s. Sorry? Yeah, it is a Higgs Lagrangian. It is exactly the same Lagrangian as for the Higgs. Okay. Now, let us focus on the Lagrangian for the Goldstone bosons, which we thought of discussing today. Suppose I work in energies much less than the mass of this s field m, then I can integrate out the s field. Okay. So, then at the leading order the Lagrangian for the Goldstones becomes v square over 4 trace del mu u dagger del mu u, right. Integrating out at leading order means you can simply erase this. Okay. At higher orders, of course, you have to compute s exchange diagrams and see which operators they give, right. So, this is the leading order term in the Lagrangian for the Goldstone bosons, and you see that they involve this term involves two derivatives. So, whatever couplings that we are going to get for Goldstone bosons will involve at least 2 derivatives, right. Now, having derivatives in interaction means in the Feynman rules you will have momentum factors, right, or energy factors, right. So, the leading contribution will be of order E square, right, because of the 2 derivatives in the amplitude level, right. In particular, as E goes to 0, the amplitude for Goldstone scatterings will go to 0, right. In fact, this dependence on the energy gives us a handle on this expansion in terms of effective operators for Goldstone boson scatterings, because at low energy the couplings become weak, they are proportional to the energies, right. So, we have an expansion, right. The expansion will be as a series in E over V, right. As we will soon see, all the interaction terms will come with factors of 1 over V square, okay. So, it will be an expansion in powers of E over V, and at low energies this is a controlled expansion, right. Otherwise, there are infinitely many terms actually in this trace of del mu u dagger del mu u. So, already at leading order there are infinitely many interaction terms. Let us see what those are to begin with. So, if you expand this term with u equal to e to the power I over v tau dot phi. So, you just expand, you will obtain the following kind of terms. So, this is the Goldstone Lagrangian, half del mu phi dot del mu phi. So, the factors that we have put in like v square over 4 which came in our calculation are all correct, because our kinetic term has the canonical normalization which we must recover. Okay. The first interaction term will be a 4 Goldstone interaction involving 2 derivatives. And then there will be a term of this form and so on. So, what I am doing is I am simply expanding this u as a Taylor series, right, taking the derivative, multiplying them up and getting these terms. So, I kept only up to the squared term in the expansion and got these terms, right. If you keep higher and higher terms, you will get interactions. So, this is already 4 Goldstone interaction. So, 4 Goldstone, let me write gold for short, but yeah, and 6 Goldstone, 8 Goldstone and so on. Now, you see that they come in even numbers, right, 4, 6, 8 and so on. So, it is another exercise to figure out why they come in even numbers, but can you guess? What can be the reason that the odd terms must vanish? Huh? Yeah, what kind of symmetry will lead to the odd terms vanishing? Huh? You said Z2? No, it is a parity actually. So, you will see that this Lagrangian has a parity symmetry, and these Goldstones are actually parity odd. Yeah. So, because of parity, but first do the computation and see that the cubic and all those odd terms are 0, then go back to the Lagrangian and see that parity is symmetry. The important point to note is that phi right, but phi dot phi, all the phi's transform in the same way under parity. The remnant symmetry is there of course, but parity is also a symmetry, and that actually prohibits the odd terms. I do not think the vector symmetry will prohibit the odd terms. So, please check. The important point to note is that all these 4 Goldstone, 6 Goldstone, 8 Goldstone, all these interactions at this order are given by a single parameter v square, right. So, all these interactions at this order are fixed by v square. So, if I can somehow measure v square, right, by measuring the amplitude for a single process, then I will know the amplitude for all the other processes, right. Okay. Now, so far the discussion was quite generic. What does this have to do with QCD? Right, this was just a model, right. There was no QCD here, right, but I still claim that this is not electroweak. You can still understand, right, everything looks like the Higgs symmetries, so that is okay. These are this is the Lagrangian for electroweak Goldstones as well, right. But what does it have to do with QCD? Now, originally the fact that this is also low energy Lagrangian for meson scattering came from understanding the phenomena of mesons and realizing that the low energy phenomena of mesons and mesons obey this kind of a symmetry breaking pattern. Okay. So, low energy meson phenomena, right, because they did not know about QCD at that time, right. So, the study of these currents that I mentioned. However, since we know about QCD, let us just look at the quark part of the Lagrangian for QCD. So, L quark in QCD, right, is q bar I d slash q. Oh, QCD with mass of quarks as 0, QCD with MQ0, and just consider 2 flavors. So, consider q equal to ud, 2 flavors. So, these q's are column in this flavor space, right, this just u and d. They also have color indices, but I am suppressing those color indices. Okay. Now, this is same as ql bar I d slash ql plus qr bar I d slash qr, right. You can easily check this. You know what this L and R mean, right? It's 1 minus gamma 5 by 2 is PL and so on. Okay. Now, you can immediately see that this Lagrangian has this SU2L cross SU2R symmetry, under which this QL transforms as GL QL and the QR transforms as GR QR, 2 independent SU2s, right. These matrices GL and GR are in the flavor space, 2 by 2 matrices. They do not act on the Dirac indices or the color indices, they just act on the flavor indices, this U and D, right. And it turns out that the spectrum of low energy, spectrum of mesons that we see, they do not have this SU2L cross SU2R symmetry. Okay. So, the symmetry of the Lagrangian is not respected by the spectrum. Now, the spectrum reflects the symmetry of the vacuum, because the mesons that we see are excitations over the vacuum, right. And the mesons show a single SU2 symmetry, so called SU2V. So, therefore, the spectrum implies that this SU2 left cross SU2 right symmetry that exists in the Lagrangian is actually broken to SU2V. Now, given the fact that the symmetry breaking pattern is the same as we studied before, even though this is not the same model, it's a theory with quarks, right, which eventually become mesons after confinement, still because the symmetry breaking pattern is the same, all the Goldstone dynamics is the same, as we emphasized. So, the Lagrangian that we wrote down, this Lagrangian, must be the leading order Lagrangian for pions. So, if you want to compute pion-pion scattering, you can compute it at leading order just by using this Lagrangian. Okay. And the symmetry breaking happens in a very different way in QCD. It is believed to happen through a condensate of Q bar Q, which breaks this SU2L cross SU2R. Right? The mass term breaks SU2L cross SU2R. Q bar Q respects SU2V. Okay. So, the mechanism of symmetry breaking is very different, but as I emphasized earlier, it is just the symmetry breaking pattern that determines the low energy Goldstone boson scattering Lagrangian. Right? It does not matter how the symmetry was broken. As long as the G and the H are the same, everything is same. So, the low energy scattering of pions is described by exactly the same physics as for the electroweak Goldstones. Yeah, just let me complete and then we'll come back, because you're running here. Okay. Now, before I end, I'd like to give you two more exercises. The first one is that now we have a Lagrangian which shows that Goldstone boson scattering at leading order should go as E square. So, if you compute with this Lagrangian now, pi pi to pi pi scattering, that should have a leading behavior of E square, right? And because the Lagrangian has two derivatives, right? But remember this Lagrangian we started with, there was no derivative at all for the Goldstone interactions. It was all cubic and quartic interactions. And I gave you the exercise that compute the pi pi to pi pi scattering with that Lagrangian, do an expansion in E over m, and find out the leading term in the energy expansion. So, you already know the answer you should get. It should be proportional to E square. This Lagrangian makes it very clear. It makes it very clear because we chose our coordinates very carefully. We chose the angular directions as our Goldstone coordinates, right? And the moment you choose the angular directions as your Goldstone coordinates, the symmetry of the theory of the vacuum is reflected as a shift symmetry, right? The angles shift under these rotations, and because the Lagrangian should be shift symmetric, it can only contain derivatives. Right? In the previous Lagrangian, this fact was hidden. Right? So, as long as you do that computation correctly, the leading behavior should be E square. And now you know how to write down the higher terms that Jose had written, right? The next terms will contain even more number of derivatives. So, try to write down terms with 4 derivatives, right? You can think of all the possible terms that you can write down. Okay. Lastly, I would like to end with what I started with. I said that low energy pion scattering, Weinberg said, obeys an interaction Lagrangian of the form pi dot del mu pi whole square by v square minus pi dot pi. But this looks very, very different from what we wrote here. Is trace of del mu u dagger del mu u. So, there must be another field redefinition that gives you this Lagrangian. So, I want you to determine the field redefinition that will lead to this Lagrangian starting from the initial sigma model that we had written. And a hint in this respect is the following. If you think about it carefully, if you have a SON symmetry which the old sigma model had broken to a SON minus 1 symmetry, then the Goldstone bosons live on the surface of a sphere Sn minus 1. Okay. This you can show. Just study the equation describing the Goldstone bosons and they live on the surface of a sphere. So, they are constrained to live on the surface of a sphere. Now, the surface of a sphere is described by an equation of the form pi 1 square plus pi 2 square up to pi n square equal to v square. The radius of the sphere is this v. Okay. The radial excitations are actually change in the radius of the sphere, and the Goldstone excitations are all movements on the sphere. Okay. So, you have a constraint equation pi 1 square plus pi 2 square up to pi n square is equal to v square. Right. But with constraints fields, you cannot do your quantum field theory. You have to choose a set of independent fields. So, eliminate one of the fields by using this equation. Right. You can immediately see, so suppose you eliminate pi n, right. So, pi n square can be written as v square minus pi 1 square and so on. And given that, this Lagrangian immediately follows. So, just complete the steps and we'll come back full circle. Okay. So I like to end with that. Thank you. Yeah, now we can come back.
Questions? Yeah. Sanjay.
No, you just said that the quark mass term break the symmetry. You said, right?
Quark mass terms do not respect the SU2L cross SU2R symmetry.
Yeah, but anyway, that was already broken by the vacuum expectation value of the QQ bar bound state, right? Spontaneously.
Well, I mean,
that was explicit breaking.
Yeah. So this step came before. So why I was not writing the quark mass terms to begin with, right? Because they break the SU2L cross SU2R symmetry explicitly, and now we don't know what the QCD dynamics does, right? So it must be, whichever way the symmetry is broken, it must be through the vacuum expectation value of an operator, right? Now this operator QR bar QL actually breaks the axial vector symmetry, and we know that the axial vector part is broken. So this is the simplest operator that will break the axial vector symmetry and keep the vector symmetry intact, which is realized in the meson spectrum. There can be other operators, right? But people have calculated these operators on the lattice, right? And it seems that you can have chiral symmetry breaking through expectation value of the operator. But unless we do non-perturbative physics, we have no idea to know. But this is the simplest operator that will break the axial vector symmetry. We already had some discussions, but if you have more questions.
More questions?
So I hope I made this point home that the Goldstone boson Lagrangian represents everything that you have learned about effective field theories. You have a low energy symmetry, you know the low energy degrees of freedom, right? The low energy symmetry is whatever this H, the low energy degrees of freedom, the Goldstones, and just the symmetry breaking pattern determines the Lagrangian for the Goldstones. This is IR physics, right? This says nothing about the UV physics. The parameter that is sitting there, the V, that is determined by the UV physics. That is different in the standard model and in QCD, right? In standard model is 246 GeV, in QCD is 130 MeV, okay? That is determined by the UV physics, but the effective field theory doesn't know about the UV physics, okay? It's only the IR physics that knows. And it's a controlled expansion. In this case, the controlled expansion is in powers of E square over V square, right? So you can write down many more terms, you can calculate loops also, right? Still it will remain a controlled expansion. Of course, the loop diagrams will be divergent, you cannot absorb all of them at a certain order, you need to include higher order terms, but once you do that, again it will become renormalized, right? So it's a very controlled theory where you can make predictions, compare with experiments, and it's a quintessential effective field theory. B.
So is it related to QCD scale?
It's the pion decay constant.
Okay.
Yeah. Right. So usually it's determined from the decay width of the charge pion because it couples to this axial current. Yeah.
So I thought about that alpha running of QCD that starts diverge around lambda equal to 20.
Similar scale, but here it's the pion decay constant. Yeah, there's a question.
Is it correct to say that this SU2L cross SU2R is equivalent to SU2 axial vector cross SU2 vector, and then when the quark gets the condensation happens, this axial part SU2 axial is basically broken down.
Correct. So the vector generators are L plus R generators, axial are L minus R generators. So it's correct.
Okay.
You can work with both of them. The commutation rules will be different, right, depending on what you choose, right? So in the SU2R, L cross SU2R thing I wrote down, the commutations are especially simple, right? But in the one you said, they get mixed up and then it will be different. Yeah. But the physics is the same, you're right.
Can you write a flavor changing operator and match with this chiral perturbative Lagrangian?
No, so I am trying to describe mesons.
Yeah.
And the theory that I did was SU2 cross SU2. So it just describes pions, right? So all the interactions of charged and neutral pions are described by this Lagrangian.
So like in QCD, so there is a U and D quark
Yeah, but this Lagrangian is not about U and D quarks. It's about the low energy degrees of freedom.
Low energy degrees of freedom.
Pions.
So if you take some corresponding Wilson coefficient and their flavor changing operator that it mixes with U and D.
We
I
cannot-
mean not U and D, like yeah.
No, so,
So-
as I said, pi plus, pi 0 can have scattering amplitudes which are non-zero. This describes all of this, right? What you are trying to suggest is that there is a flavor mixing in the QCD Lagrangian. That is not the case. The QCD Lagrangian has no flavor mixing.
So not at the tree level, but as the effective operator, like some loop
Higher
suppression
dimensional
operator. Yeah.
You may write down, but I don't know what that will do because we cannot match. See, I began with the fact that there are theories in which you cannot match and there are theories in which you can match. We are discussing a theory in which we cannot match, and it's only this global symmetry breaking pattern that we can see in the low energy mesh.
Only diagonal quarks are there in that case.
Yeah, the QCD Lagrangian has only diagonal.
Yeah.
More questions?
So maybe after you do the exercises, you might have more questions. I'm around. So please
Yeah,
catch me. And,
So
also
2
this-
more days to go, so you have time to finish those exercises also. Okay, if no more questions, let's thank
thank you.
Shotto for a nice talk. And we would like to do the honor of felicitating him. So that was a nice session to know that many of you have traveled long distances to come to this part, and hopefully we are not boring you to a great extent, and it has been a fruitful 3 days so far. So we next couple of days will be exciting as we go along, and we have 4 more lectures by Jose and 2 by me, and we have 2 more guest lectures, as you can imagine, one by Shankho, who will talk tomorrow, and Shoumitrada is going to finish on the last day. So okay, with that note we finish today, and we see you tomorrow. Have good rest and enjoy the evening.